Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 21 of condensed matter physics. Okay. So this is the part third of the superconductivity I'm discussing. Okay. So okay. Also, guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. And also, guys, please share my lecture details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, so let's get started, guys. Meanwhile, just let me check whether I'm audible or not. My free live lectures. Yes, I'm audible, so I'll proceed further. Okay. Okay, guys. So first I'm discussing flux quantization. Okay. Flux quantization. Flux quantization. So what is flux quantization? Okay. So we have a super this superconducting wire. Okay. So the ring, superconducting ring. Okay. So it's superconducting ring, SC ring in short, I can say. Superconducting ring. Okay. So we the magnetic field is applied on this ring. So what happens is the magnetic field will go outside of the ring because the superconductor is this is perfectly diamagnetic, and we know for superconductor, perfectly diamagnetic superconductor, V in is 0. Magnetic field inside is 0 because when we apply magnetic field magnetic field through the superconductor, it it does not penetrate it, it passes outside of the superconductor. Okay, but if we talk about normal conductor, if you pass the magnetic field, the field line will pass through penetrate the conducting the superconductor. Okay. Okay, so these are the magnetic field lines which passes outside of the superconducting ring. Okay, and this is at T equal to 0 Kelvin. Okay. So we have applied external magnetic field, right? External magnetic field. So when we applied external magnetic field through the superconducting wire or superconducting ring, so what happens is the magnetic field lines passes outside of the superconducting ring, and doesn't penetrate the superconducting ring. Okay, so because of that, the B inside is 0. Magnetic field inside the superconducting ring is 0. Okay, so this is the case, guys. But when we remove the external magnetic field, okay, so this is the case. This is the superconducting ring, circular ring. It's a circle, guys. Okay, circular ring. Consider it is a circle. Okay, circular ring. So what happens is when we remove the remove the external magnetic field, external magnetic field is removed. So when we remove it, so at 0 Kelvin, okay, so it is at T equal to 0 Kelvin. When we T equal to 0 Kelvin. Okay, so when we remove the external magnetic field, so what happens is the some part of magnetic field gets trapped. Okay, the magnetic field, the magnetic field gets trapped inside the conducting superconducting ring. Okay, this is happens, right? So this is superconducting ring, right? SC ring in short, I'll say. So when we apply the external magnetic field, in that case the magnetic field line passes outside of the superconducting ring. Okay, but when we remove that external magnetic field, then what happens is the part of the magnetic field gets trapped in the superconducting ring. Okay, so this gets trapped. Okay guys, so now I'll write it. Okay, so and also guys, here the trapped flux, so the magnetic flux gets trapped inside the superconducting ring, right? So that trapped flux is that trapped flux trapped flux is nh upon 2e, that is equal to nh upon 2e, nh upon 2e, where n is the integer. Okay, n is integer, so this trapped flux is equal to nh upon 2e. Okay, okay, so flux of flux of flux trapped on the removal of external magnetic field, flux trapped on the removal flux trapped on the removal of external magnetic field of external magnetic field. Okay, flux trapped on the removal of external magnetic field. So this is the flux trapped. Okay, so the flux trapped on the removal of external magnetic field, okay, is always important point guys. Okay, it is always an integral and integral multiple of h upon 2e, right? So here I have shown you this one. The trapped flux is nh upon 2e, where n is the integer, right? So that's why the flux trapped on the removal of external magnetic field is always an integral multiple of h upon 2e. Okay, this one, where n is integer. Okay, so the multiple of h upon 2e. Okay, so this is the flux quantization, guys. So or we can write this flux quantization, right? The flux is quantized. So flux will be, so we get this that trapped flux in the form of this nh upon 2e. Okay, so multiple integral of this one, the this is integral multiple of h upon 2e. So flux is quantized, that trapped flux is quantized, that is the flux quantization. Okay, so or we can or that is called and this flux zone. Okay, flux zone, that is h upon 2. So this is called h upon 2e is called flux zone. Okay, or we can denote it by phi naught. This is important. Okay, phi naught, and this is also called quanta of flux trapped. Okay, or this value is called quanta of flux trapped. Quanta of flux trapped. Okay, quanta of flux trapped. So this is the flux zone. Okay, flux zone, that is h upon 2e, or we can denote it by phi. Okay, so this is so, and this flux zone is also called quanta of flux trapped. Okay, so flux is the trapped flux is quantized, and that is the flux quantization. I hope guys you have understood it. Now we know guys here that London penetration depth I have already explained in my previous lecture. Right? London penetration depth. London penetration depth. London penetration depth we know, right? That is B lambda is going to be B naught upon E, right? So B naught upon E at x equal to lambda, right? This is the at x equal to lambda, right? So that is called lambda, called London penetration depth, right? So this is we know that B lambda or B is equal to B naught upon E, right? So that is the penetration. So at penetration depth, this magnetic field is equal to B naught upon E, means 1 upon A times of the magnetic field at the surface, right? This one. So now for normal conductor, guys, for normal conductor, if you talk about normal conductor, for normal conductor, for normal for normal conductor, for normal conductor, lambda, the penetration depth lambda is infinite, guys. Okay, and ns, number of super electrons, is 0 for normal conductor. Okay, so if we talk about for superconductor, for superconductor, for superconductor, for superconductor, this one, for superconductor, this lambda value, that is penetration depth, that is going to be, okay, that is going to be root m upon mu 0 nse square. Okay, nse square. Okay, this lambda value for superconductor is this. Okay, that is penetration depth. So root m upon mu 0 nse square, right? Or we can write, that implies lambda is proportional to 1 upon root ns. So lambda is proportional to 1 upon root ns, means number of, where ns is number of super electrons. So the penetration depth in case of superconductor is proportional to 1 upon root ns. Okay, okay guys, so this is the one. This is important to tell, guys. Okay, next is coherent coherence length. Okay, coherence length, coherence length, coherence length, coherence length, coherence length. Okay, so what is coherence length, guys? Okay, so ns is this here, ns is number of super electron. Okay, I have explained this in my previous lecture. Number of super electrons. Okay, So lambda is infinite for normal conductor and lambda is proportional to 1 upon root ns for superconductor. Okay, important result. So coherence length. So what is coherence length, guys? Okay, coherence length is denoted by zeta. Okay, zeta, and so definition is the distance up to which the distance up to which the distance up to which super electron concentration okay, the distance up to which super electrons concentration does not change or doesn't change drastically, doesn't change drastically. Okay, so coherence length is the distance up to which super electrons concentration, okay, doesn't change drastically. So that doesn't change drastically, that length, okay, the distance up to which the super electrons concentration does not change drastically, that distance is called coherence length. Okay, and mathematically it is denoted as this one: zeta is equal to 2h cut vf 2h cut vf upon eg. Okay, 2h cut vf upon eg, important result. And where vf is Fermi velocity. Okay, Fermi velocity, vf is Fermi velocity. Okay, and eg, the band gap, that eg value is 3.5 kbtc. Kb is Boltzmann constant, important one. Okay, this one, eg equal to 3.5 Eg equal to 3.5 kbtc. Okay, Tc is the transition temperature and Kb is a Boltzmann constant. So Eg, that band gap, is equal to 3.5 kbtc, or that is almost equal to, we can write, this is almost equal to 4 kbtc. Okay, 4 kbtc. Okay, guys. So this is the coherence length. Now this is important one, guys. This one, this for type 1 semiconductor, for type, I have explained type 1, type 2 semiconductor earlier. Okay, so for type 1 semiconductor, you need to know, for type 1 semiconductor, the zeta, that is coherence length, is greater than lambda, that is greater than lambda is penetration depth. Okay, this one, penetration depth. Okay, so for type 1 semiconductor, the zeta, that is coherence length, is greater than lambda. Okay, zeta is greater than lambda. Okay, and now for type 2, these are very important points. For type 2 semiconductor, zeta is less than lambda. Okay, zeta is less than lambda. Okay, so the coherence length is less than penetration depth, and this one is asked in CSIR net. So it's important. Okay, so this is asked in CSIR. Okay, so this is for type 2. For if we talk about type 2 semiconductors, in case of type 2 semiconductor, the zeta is less than lambda. Okay, and for type 1 semiconductor zeta is greater than. Zeta is means coherence length and lambda is penetration depth. Okay guys, next is Josephson effect. Okay, Josephson effect or Josephson effect, that is Josephson 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 effect. Okay, Josephson effect. Josephson effect. Okay, so it's important one. So okay, this is superconductor and this is superconductor guys. And this is insulating layer. Okay, Josephson effect, it's insulating layer. Okay, this one. Insulating layer. Insulating insulating layer. Okay, so this is insulating layer guys. Okay, so when an insulator when an insulator insulator when an insulator is sandwiched when an insulator is sandwiched between two superconductors when an insulator is sandwiched between two superconductor two superconductor two superconductors, then it is known as it is known as Josephson effect. Okay, known as Josephson effect. Joseph Joseph Josephson Josephson effect. Okay, sorry, this is called then and it is known as Josephson this one junction. Okay, so this is the Josephson junction. Okay, so what we have done is, so the insulating layer is sandwiched between two superconductor. Okay, so that is the so when then in that case this is this layer is called Josephson junction. Okay, okay, next point is Cooper pair can can transmit Cooper pair can transmit through Cooper pair can transmit through insulating layer. Insulating layer. Okay, by tunneling effect. Okay, so Cooper pair electrons can transmit the Cooper pair electrons of the superconductor can transmit through insulating layer. Okay, by tunneling effect. So okay, so this is the Josephson effect. Okay, and this is Josephson junction. So now there are two types of effects. Okay, So there is the first effect is number one. It is in two part. Okay. So this is DC Josephson effect. Okay. DC Josephson effect. Okay. The first is DC Josephson effect. Okay. So that is DC direct current. Okay. So in that case, what will happen? So there are points. First point is no external source. Okay. No external source. Okay, no external source, so there is no external source applied. Okay, here it is just we have sandwiched the insulating layer between two superconductors, and no external source is applied. Okay, so no external source. Second is in absence of electric field, or we can say in absence of electric field or magnetic field. Okay, so no external source and in absence of electric field or magnetic field. So there is no electric field or any magnetic field, or there is no external source. Okay, so in that case there would be DC Josephson effect. Okay. Okay, so here the value of J is going to be J naught sine delta, important. Okay, J equal to, this is the in case of DC Josephson effect. Okay, this one, and where delta is phase shift. Okay, delta value is phase shift. Okay, and without that, so what will happen is the current flows, DC current will flow. Okay, DC current flows through the junction. Okay, flows through the junction. Okay, so here so there is no external sources, no magnetic field, no electric field. Okay, no potential. So in that case, what will happen is DC current will pass through this junction. Okay, so so this is the case of DC Josephson effect. Okay, so this is the one. Next is, and this is important formula, guys. Okay, J equal to J naught sine delta, where delta is phase shift. Okay, next is AC. Second is AC Josephson effect. Okay, AC Josephson effect. AC Josephson effect. Okay, so here the points are, so here external voltage. Okay, external DC voltage. We will apply external DC voltage source. Okay, so external DC voltage source, external DC voltage source is applied. In this case, in this effect, so we will apply the external DC voltage source. Okay, external DC voltage source is applied. Okay, and so in that case, what will happen? So we have, so this is the insulating layer, right, which is sandwiched between two superconductors. Okay, so what we have done is in AC Josephson effect, we have applied, we have connected with the external voltage source, means we have applied external voltage source. So in that case, what will happen is AC current will flow in this flow through the junction. Okay, so AC current, AC alternative current. Okay, AC current, AC current flows. AC current flows. Okay, so here frequency of the current. So frequency of current is frequency of current. Frequency of current, that is omega equal to 2 EV upon h cut. This is very important formula, guys. There is a 5 marks question which is we have got in the CSIR net exam. Okay, and using this, so you can easily get that answer by using this formula. Okay, so frequency of current is omega equal to 2 EV upon h cut. Okay, where V is this voltage. Okay, external voltage which we have applied. Okay, 2 EV upon h cut, 2 EV upon h cut, and E is the charge of electron. Okay, so this is very important formula you note down, because we have a question asked using this formula in the examination in CSIR. Okay, I have solved that question as well in my this paper series which I'm solving. Okay, so this is the important result, guys. You need to note down. So this is for AC Josephson effect. Okay, next is so in case of this AC Josephson effect, J is equal to J naught sine delta minus omega. Okay, delta minus omega, where omega is frequency, and that I have already explained this one. Okay, so this is the AC Josephson effect, guys. Okay, and here J equal to J naught sine delta minus omega t. J equal to J naught sine delta minus omega t. Okay, well, next is there is a question which I'm going to solve. Important question. Just wait. So question is, just give me 1 second. Okay, so question is, the penetration equation, the penetration the penetration equation may be written as delta square del square B equal to B. Okay, B is the magnetic field. Okay, and lambda is penetration depth. Lambda is penetration depth. Find out Bx, that is magnetic field inside a superconducting plate. Okay, superconducting plate perpendicular to the x-axis, perpendicular to the x-axis, and of thickness delta is. Okay, options are given. Option A is Bx proportional to cos hyperbolic x by lambda upon cos hyperbolic delta by lambda. Okay, option B is Bx is proportional to cos hyperbolic x by lambda upon cos hyperbolic delta upon 2 lambda. Okay, option C is Bx is proportional to cos hyperbolic x by lambda upon cos square hyperbolic delta by lambda. And option D is Bx is proportional to cos x by lambda upon cos square hyperbolic delta upon 2 lambda. Okay, so this is the question, guys. Very good question. So I'll read this question for you. Question is, the penetration equation may be written as this. So we have been given penetration equation. Okay, and lambda is the penetration depth, and find out the Bx inside the superconducting plate. So we have to find out magnetic field inside the superconducting plate, which is perpendicular to x-axis, and thickness delta is, and thickness is given. Okay, thickness delta is. So we have to find that B. Okay, very simple. Okay, and this is the figure. This is this one. This is the figure given. Okay, this one. This is x equal to 0, and this is x equal to minus delta by 2, and this is x equal to delta by 2. X equal to minus delta by 2. Okay, this is the figure. So now I'll solve it, since we have been given that this is lambda square delta square b equal to b. This is what we have been given. Okay, b is the magnetic field. Okay, so from here we can write delta square b equal to b upon lambda square. Okay, so now we have delta square b equal to b upon lambda square, right? And so we'll solve it. Okay, so it's two second order differential equations. So let we can solve it by let b equal to e to the power mx. Okay, b equal to e to the power mx. So from here del b upon del t is del x is going to be del b upon del x. Okay, del b upon del x. We have to find bx, right? So del b, so b is the function of x. So del b upon del x is going to be m e to the power mx. So similarly, again we'll differentiate it. Del square b upon del x square is going to be m square e to the power mx. Okay. So from here, so this is suppose equation 1. So this equation we can put here. This is equation 1 or this is 2. So from 2 we can put this value. Okay. So from 2 we can put this value in 1. So this means it is going to be m square, right? We can write this one for this. This is del square b equal to m square e to the power mx. So we'll put this value. We will put this value in the equation 1. So this is going to be m square e to the power mx equal to b upon lambda square, or we can write m square e to the power mx equal to b value is this is e to the power mx upon lambda square. Mx will get cancelled. So m square equal to lambda square, that implies value of m equal to plus minus lambda. Plus minus 1 upon lambda. Plus minus 1 upon lambda. So from here, this we have got the value of m, right? So from here, the solution for this differential second order differential equation is going to be that this one, b equal to very good question, guys. Okay, b equal to, this is going to be a e to the power of this one, x by lambda. Okay, x by lambda plus b e to the power minus x by lambda, e to the power minus x by lambda. Okay, so this is the important result, right? Equation number 3. So now we'll get the value of a and b, and then so we'll use the boundary condition here. Okay, at x, so at x equal to minus delta by 2 and at x equal to delta by 2, this value of b is going to be b naught. Okay, so this means at, from the figure, okay, at x equal to delta by 2 or x equal to minus delta by 2, value of b is going to be b naught. Okay, value of b is going to be b naught at this boundary condition. Okay, at this boundary, value of b is going to be b naught. So now we'll put values. Okay, so this means for x at x equal to this delta by 2, b equal to b naught, right? So at x equal to delta by 2 implies value of b equal to b naught. B naught is going to be a e to the power, we'll put here in equation 1, right? In place of x, we will write delta by 2. So this is going to be a e to the power delta by 2 lambda plus b e to the power minus delta by 2 lambda. Okay. Similarly, at x equal to minus delta by 2 implies b naught is going to be, this is I'm writing, this is a constant, right? There are b as well, magnetic field, so c I'm writing. Okay, so a e to the power, this is minus, means e to the power minus delta upon 2 lambda plus c e to the power minus delta upon 2 lambda. Okay, this one at x equal to this and at x equal to minus delta by 2, this one. So now if we solve it, these two, so these values are equal, right? So these values are equal. This is this one, equation 4, you can say 4 and 5. So if we solve these two, okay, we'll put these values equal to, then so if we solve 4 and 5, we are going to get a equal to c. Okay, so from here, so we can write b naught equal to a e to the power delta upon 2 lambda plus a equal to c means a e to the power minus delta by 2 lambda, right? So from here we can get value of a. Value of a is going to be b naught upon e to the power delta upon 2 lambda plus e to the power minus delta upon 2 lambda, right? Or we can write this is cos, because e to the power x plus e to the power minus x is cos 2 cos hyperbolic x, right? So this value is going to be b naught upon 2 cos hyperbolic delta upon 2 lambda. Okay, so similarly, so this is equal to c. Value of c is also same. Now we'll put the value of a and c. Value of a and c in the same thing is in equation 3. In equation 3 to get the required value, right? So b is going to be, it means b is going to be, if you put the value, so this is a e to the power x upon lambda plus b e to the power minus x upon lambda, right? So value of b is going to be, sorry, this is c, and a and c are same, right? I can write in place of c, I'll take common a, so I'll just put the value of a. This is b naught upon this one cos 2 cos hyperbolic delta upon 2 lambda, delta upon 2 lambda. Okay, and this is going to be e to the power x by lambda plus e to the power minus x by lambda. Okay, so value of b is going to be, so here again e to the power x plus e to the power minus x, that is equal to 2 cos hyperbolic x, right? So b naught into 2 cos hyperbolic x by lambda, okay, upon 2 cos hyperbolic delta upon 2 lambda, right? 2 will get cancelled, so this value is going to be b naught cos hyperbolic x by lambda upon cos hyperbolic delta upon 2 lambda, right? So from here b is proportional to this one, b naught, so b is proportional to cos hyperbolic x by lambda, cos hyperbolic x by lambda upon cos hyperbolic delta upon 2 lambda. Okay, so this is b is proportional to this. Okay, b is proportional to this, and this is the answer. So which option is matching? Here you can see this one. This one, option B, B equal to cos hyperbolic x by lambda upon cos hyperbolic delta upon lambda. Okay, so this is the answer, guys. It's a good question. I would request you to practice this question. Okay. Okay, guys. So I'm going to stop here, and also, guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. And also, guys, share my details, lecture details, to your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, guys, thank you so much. Bye now.